Airspeed, 228 knots. Altitude, 29 feet. How fast and how low can rotary wing aircraft be flown over various types of terrain? How susceptible is the aircraft to ground observation? In October 1967, Lockheed embarked on a test program to investigate low-level flight in rotary wing aircraft, often called nap of the earth flight. The aircraft used were the Lockheed L-286 rigid rotor helicopter and the XH-51A compound, a research vehicle which also employs the rigid rotor system but combines it with a stub wing and forward thrusting jet engine to provide increased speed. This aircraft has flown in excess of 300 miles per hour. Both aircraft were instrumented to provide continuous measurement and recording of airspeed, altitude, and control response information. A cockpit camera was mounted to photograph the instrument panel, and another to simulate the view of an observer sitting behind the pilot. Accurate measurement of tape line altitude was obtained with a radar altimeter. 3 different flight corridors were selected for the test run courses in an area northeast of Lockheed's test facility at Oxnard, California. A flat terrain corridor that ran along the Santa Clara River between the cities of Satacoy and Fillmore. A rolling terrain corridor situated between South Mountain and the Camarillo Hills. And a rough course that started at the base of South Mountain and traveled along the ridges. Each course was approximately 20 nautical miles. 24 data runs were obtained on each corridor, 12 for the compound and 12 for the L-286, a total of 72 in all. Speeds of 50 to 125 knots were assigned to the helicopter. While speeds of 150 to 225 knots were set for the compound. During each run, the pilots flew as close to the ground as terrain and atmospheric conditions permitted, consistent with flight safety. Observer teams and cameramen recorded both oral and visual detection time of the aircraft to determine the degree of susceptibility to ground observation. Terrain of the flat corridor was comprised mainly of river bottom, broken by trees and shrubbery. Since this terrain had few obstructions, only minimal maneuvers were required. Ground observer posts were located to simulate typical ground-to-air weapon emplacements. Although experienced in aircraft tracking, cameramen still had extreme difficulty in following the fast-flying compound. Over this flat course, the pilots had little difficulty in maintaining low altitudes. Even at the higher speeds of the compound, altitude increased only slightly. But the payoff from higher speed was quite evident in decreased aircraft exposure time. A reduction of 65% was noted over the 50-knot run. The rolling terrain corridor consisted of gentle to moderately sloping hills with good separation between the peaks. Air turbulence varying from light to heavy was encountered on every flight over this terrain. However, the excellent damping characteristics of the rigid rotor control system alleviated this otherwise serious problem. At the higher speeds of the compound, both test data and pilot comments indicated high maneuverability and ease of handling, which provided comfortable margins of safety for maneuvering. In many instances, bank angles in excess of 90 degrees were recorded. The average altitude over rolling terrain reached a low of 45 feet at 50 knots and increased to 140 feet at 225 knots. As in the flat course, increased airspeed reduced exposure time despite the slightly higher altitudes. The rough terrain corridor contained closely spaced mountain ridges and canyons, intersecting the flight path at various angles. At low speeds, the helicopter did not have sufficient zoom capability or power response to conduct low-level operations safely in the mountain turbulence. Navigation problems were encountered. Several flights were aborted when the pilots became lost flying circuitous routes through the canyons. In contrast, the compound was able to fly a more direct route, using its J60 auxiliary thrust and superior zoom capability to good advantage. This plot of average exposure time versus airspeed shows that for all three terrain types, rough, rolling, and flat, exposure time decreases as airspeed goes up. It also shows that as airspeed is increased from 50 to 225 knots, average exposure time decreases from 60 to 70%. Note the sharp decrease in exposure time for the compound over rough and rolling terrains. This abrupt decrease verifies the superior turning and climbing performance of the compound. With its stub wing and independent forward-thrusting jet engine, the compound was able to take full advantage of terrain concealment. However, the helicopter was unable to negotiate the extreme elevation changes without sacrificing airspeed. In order to maintain nap-of-the-earth altitudes, pilots were obliged to fly devious routes and thus were in the observer's field of vision for a considerably longer time. Now, let's look at these test results in terms of survivability. Though the decrease in exposure time at the higher speeds of the compound appears relatively small, can it really offer a tactical advantage? To give perspective to this question, Lockheed assumed two hypothetical combat situations. A rotorcraft is being fired upon by two separate ground-to-air type weapons. First, a squad of semi-automatic rifles. And second, a machine gun. Using data from this test program and commonly employed methods for calculating survivability, the results, shown in numbers of sorties flown at 80, 150, and 225 knots before aircraft attrition, strongly indicate an advantage for the faster compound aircraft. Increasing the airspeed from 150 to 225 knots triples the expected number of sorties against both the machine gun and semi-automatic rifles. A survivability analysis must be conducted for each specific rotary wing system. However, the message is clear. Low-level flight in compound aircraft offers important survivability benefits. The Lockheed rigid rotor compound, with its forward-thrusting jet engine, has the control power and speed needed for superior nap-of-the-earth flight. In addition, its zoom capability offers an important advantage in aircraft safety, as well as in maneuvering. In the event of engine failure, its ability to gain altitude before landing significantly increases its chances of survival. These demonstrated advantages are incorporated in the Army's AH-56A Cheyenne and will be reflected in future generations of Lockheed rigid rotor craft, including military transports, now in the design and developmental stage.